Everyone, whoa, kicks in and brightens me a little bit. I'm handing the microphone over to one of the CERIAS student ambassadors, Kevin May, and he's actually going to do the introduction for us.
Yeah, hello everyone. Hello everyone. I'm Kevin May, sophomore in pre-university studying cybersecurity and network engineering. And I'd like to introduce Professor Tao Li of the Department of Computer and Information Technology, and he's here to present his topic, securing smart sensing against physical adversarial AI attacks. And I'd like to once again, show Dr. Yep.
Thank you for the introduction. Hello, can you hear me? Okay, perfect, thank you. Probably I need a clicker, right? Oh. Which one? Okay. Okay. Okay, good. Good afternoon, everyone. My name is Tao Li. I'm currently an assistant professor in the Department of Computer and Information Technology in Purdue, Indianapolis. Yeah, probably I'm the only speaker from Purdue, India. Thank you for inviting me to be here. So today, my research mainly focuses on the security and privacy in a wide range of sensing systems. So today, I'm very happy to share my research on securing smart sensing against physical adversarial AI attacks. Specifically, I will discuss one of the physical AI attacks, that is the physical backdoor attack on the wireless human sensing system. Okay, let's continue. Okay, so first, what is smart sensing? Smart sensing actually integrates three different components. That is sensing, intelligence, and communication. It uses intelligent sensors and novel data processing techniques to analyze and react to the physical world. And common sensors used in such systems are camera, LiDAR, radar, motion sensors, biosensors. And right now, deep learning neural networks are very popular for the intelligence part. And depending on specific devices in the sensing system, we can use different kinds of communication technology like 5G, Wi-Fi, Bluetooth, and Zigbee, right? Zigbee is widely used in IoT communication. And smart sensing actually has a lot of applications. For example, autonomous driving, right? The AV system use sensors like camera, radar, LiDAR for sensing. And then we use AI model for object detection and decision making on the road, right? And also the AV, it integrates, for example, 5G communication technology and also maybe vehicle-to-vehicle communication protocols, right? And also it has some other applications like smart home and smart health. For example, at our home, we have many sensors to monitor temperature, humidity, right? And we can adjust our home appliance accordingly, right? And also in smart health, we can use some biosensors to detect some health risks of the patient, right? Okay, so these are some applications. So let's talk about the secure risks in smart sensing system in the real world. Okay, so my research focused on the first two components, that is sensing and also the AI model. So first, the sensor signals can be easily tampered by the attackers, especially for wireless signals. For example, for the radar-based sensing system, it's very easy to inject malicious signals, and it's very easy to replace the signals, right? And also, when we have the signal, we need to use AI model to process, to classify these signals, right? But the AI model itself may be poisoned if the training data is poisoned, right? So based on the tampered sensor signals and also the poison AI model, actually the sensing system may generate some wrong result. For example, for an autonomous driving system, the AV may misclassify the objects on the road, right? And also, for example, for a poisoned smart health system, it may fail to detect some health risk, for example, heart attack. And also it may generate some false alarms. And also my research want to integrate, for example, the vulnerabilities in both components to launch some physical attacks. Okay, so as I mentioned, the wireless sensing system, the smart sensing system actually represents a wide range of sensing systems. So if you want to study specific attack or defenses, we need a specific prototype system, okay? So in my research, I focus on the human activity recognition system using wireless signals. So for example, we can use millimeter wave signals, we can use Wi-Fi signals to classify human activity. Okay, for example, we can use such system for the monitoring of the patients, for the old people, right, to detect the fall, right? And so this slide just shows that system architecture for the millimeter wave based human activity recognition system, okay? It has two modules. The first module is signal processing. The second one is a deep learning architecture, right? And in the actual signal processing technique is related to specific type of signal. For example, for the millimeter wave signals, we need to use some FFT, that is Fourier, fast Fourier transforms, to transform the raw millimeter wave signals to some time series heat maps or time series frames. And then when we have the time series data, we can use some deep learning models to process it, to recognize the human activity in the signal. So here I just use the CNN and LSTM model. CNN actually extracts the spatial features, and LSTM extracts the temporal features. And of course, you can use some other technique, for example, transformer and clip. So in this work, we will just based on this millimeter wave-based human activity recognition system, and all of the future attacks and defense will be based on this system. So as I mentioned earlier, we want to study the physical backdoor attack on the wireless human sensing system. But first, what is a physical backdoor attack? So corresponding to physical, actually, we have digital backdoor attack. Okay, maybe it's better to introduce the physical, the digital backdoor attack. So in the left figure, you can see an example for the digital backdoor attack in image recognition. You can see here, we want to recognize the numbers in the image, right? And we want to use the AI model to recognize these numbers. But the issue is the AI model may be poisoned if the training data is poisoned. So how to poison the data? Very easy. We just need to add some special patterns in the corner of the image. For example, you can see here, this image has a trigger here, probably you can see here. So yeah, so this is the data poisoning technique, right? So after we have the poison data, we can train the poison AI model. And then the poison AI model can consistently misclassify this image. For example, the poison AI model can classify 7 to another target number, for example, 8. Okay? So this is digital backdoor attack. So one question is why it is called digital attack? Because we just modify the digital data, the image directly, right? So for such digital attack, actually we have assumptions. That is, the attacker should be able to compromise the hosting computer of the sensing system, right? Especially in the testing phase, right? So, but now we want to consider the backdoor attack from a system perspective. So we want to enable the backdoor attack to work in the physical world without direct modification on the sample in the testing phase. So in the testing phase, we don't directly modify the digital data, okay? Then we will have the physical backdoor attack, okay? So in the physical backdoor attack, for example, in the image in the middle, we have an example for face recognition. So here you can see we can use some physical objects as triggers. So the face recognition system can misclassify a user who carries a physical trigger. That is a physical object, right? For example, the tape, the bandana, and the earrings. For example, based on the physical trigger, the point AI model can misclassify the user's face. So these are some physical triggers in the vision field. Now the question is, our topic is wireless human sensing. So what can be the physical triggers in the wireless field, right? So how to launch the physical backdoor attack for wireless-based sensing system, okay? So our basic idea is to use metal reflectors as the physical triggers to attack the wireless-based sensing systems. You can see here, we just attach the metal reflector to the human body. And then actually the wireless, for example, the radar can capture such metal reflector because metal reflector can change the radar reflection. So if we have this trigger on our body, then the sensing system can misclassify the hand gesture of this user. Okay, so let's talk about the attacker model and some assumptions in our work. So first, we assume the training data set of the system can be poisoned. Okay, actually, it can be poisoned in many ways. For example, when we train a wireless human activity recognition system, we may use some public data set. That's very common because it's very expensive to collect and label these wireless data. And also the data may be from the individual users. So the data may also be poisoned. And also we assume the attacker cannot modify the system model or data directly by compromising the host computer. Because if the attacker can compromise the host computer, then it can output any results they want. That's too strong, right? And also the attacker can train a surrogate system to facilitate the attack by collecting data themselves. So let's talk about some challenges in implement such physical backdoor attack. So if we just use a trigger, we just put the trigger at a random place, the attack performance may not be very good. So to improve the performance, we have two challenges here. The first one is how to improve the effectiveness of the attack. We want to use minimal cost in training data poisoning while maintaining high attack performance. And in the wireless human activity recognition system, we are dealing with some time series signals, time series frames, and heat maps. So we want to poison less frames and less samples in the training data, okay? So the backdoor trigger must be added to the most important frames and locations during training. And also the second challenge is our attack must be stealthy, okay? Because the attacker don't want to be easily detected either visually or through the performance degradation of clean test samples, right? Okay, so let's talk about the most important part in our work, that is to prepare poisoned training samples. So, so this process actually can be broken into two steps. In the first step, we want to identify the critical or important frames for a wireless sample. And in the second step, we want to identify the optimal location for the physical trigger for the attack. So in the first step, we use the explainable AI technique. It's called shape. So this shape technique actually can evaluate the importance of each frame, because for time series wireless signal, for time series frames, each frame does not contribute equally to the final classification result, right? So we want to choose the most, we want to choose a frame that has most significant impact on the final classification result. And we only poison these frames that has the most important impact to improve the effectiveness. And in the second step, we want to find the optimal locations on these chosen frames. So, so how to find the locations? So the objective is the reflectors on the locations must be easily captured by the AI model. So we tend to use some locations that can change the extracted feature most significantly as locations for the physical triggers. For example, this physical trigger can be a metal plate. So we just use a small plate to attach to the optimal location on the human body to fall the wireless sensing systems. And also another issue is we want to make sure the poisoned frame, the poisoned heat map should not differ too much from the original one, because we want to make it stealthy. Okay, so we use so we need to solve some optimization problem here. Okay, and during the optimization, actually we need a RF simulator to generate radar data automatically, because we cannot try every position on the human body. So this is this slide just shows the RF simulation. So the basic idea is we want to simulate the radar reflection from the human that with a reflector. The idea is to divide the human mesh into many triangles, and then we can just estimate the reflection from each triangle, and we combine them together. So you can see the stillness of the backdoor attacks. The slide shows two heat maps. Left one is clean, the other one is with trigger. So from human eyes, actually, it's hard to differentiate the two heat maps. And then we use some evaluation metrics to evaluate the attacks. For example, attack success rate, target attack success rate, and clean data rate. That's also very important because it measures the accuracy for clean samples. So you can see here we have some evaluation results. The attack success rate increases with the injection rate, and the accuracy for the clean samples always preserve high accuracy. And also we did some different combinations of techniques presented in our work. So for example, with optimal frames and optimal positions, our success rate is, for example, 84%. But with only optimal frames, but not optimal positions, it drops to 66%. If we just use optimal positions, but not optimal frames, it drops to 57%. If we use neither of them, it drops to 48%. And we also did some experiment if we hide the reflector on the clothes. But you can see here the accuracy is comparable to the metal reflector that we place outside the clothes. So we also have some potential defense for our attack. For example, trigger detection model, we can train a new model to detect the poisoned frame, the poisoned heat map. And also we can do adversarial training. We can purposefully include these poisoned samples in the training data set, but assign a correct label. And also we can do multi-sensor fusion because multi-sensor systems are much more robust than a single sensor system. But one vulnerability is some attacks actually can compromise all of the sensors. So in conclusion, we present the physical backdoor attack for the wireless human sensor systems just based on some inexpensive metal reflectors. And we use expandable AI techniques to find the optimal frames. Thank you, everyone. I can take some questions if you have.